Welcome everyone. My name is Shafiq Adams. I'm from the Water Research Commission, and I'm also part of the steering committee of the BIOGRIP platform, or the Biogeochemistry Research Infrastructure Platform, and which is a multi-agency steering committee looking after the BIOGRIP initiatives and the governance and so forth. So we've got three interesting presentations today that will take us through how can we use this platform for collaboration, its use, but more importantly, awareness building, so that more people can use these platforms. And you would also know from a water community, we've been trying to stimulate the use of the isotope toolbox in our research and in our consulting work. So without further ado, I'm going to introduce the first set of speakers, Janine, and are they ready? Yes.
Good day, everyone. Thank you for this opportunity. I will just quickly share my screen. Can you hear me, Shafiq?
We can hear you. We can hear you, Janine. Thanks.
There we go. I would just like to thank the Water Research Commission for creating this opportunity for us to tell you a bit more about BIOGRIP and the water and soil node. My name is Janine Colling. I'm from Stellenbosch University and I manage the water and soil node at the university. Sorry, I had a problem to click to the next slide. So I wanted to tell you a bit more about BIOGRIP and why BIOGRIP was established. So BIOGRIP stands for the Biogeochemistry Research Infrastructure Platform. This platform was approved in 2019, and it is being funded by the South African Research Infrastructure Roadmap and the DSR. So the idea of establishing BIOGRIP was to create technical capacity, training, and scientific leadership in biochemical research, and to provide analytical facilities which can be accessible to everyone. Finally, also to improve the monitoring of the biogeochemical environmental variables to create meaningful data sets. So the goals of BIOGRIP is to build on biochemical research, focusing on these different areas, and to set research objectives which are important to South Africa and globally. For example, water resource management, climate change, and studying the impact of human activities on our environment. The goal is also to increase the capacity of educated research professionals in the country. So BIOGRIP consists out of 4 nodes: the isotope, water and soil, atmospheric and mineral node at different universities. And all 4 nodes are being governed by the hub, which is based at UCT. Each of the nodes are being managed by different individuals, and Dr. Judith Seeley is acting director at UCT. So the BIOGRIP soil and water node is based at the Department of Forestry in Stellenbosch. And once COVID allows us again, we would like to invite you to come and visit us to see our facilities. So in the last year, we've actually installed a lot of new equipment, and this included a Metrum ion chromatography instrument and a scalar discrete analyzer, which can be used to study and quantify ions, and also other properties of water such as alkalinity, hardness, and color in soil extracts, effluent, surface, and groundwater. We've also installed a TOC analyzer from Elementa, and this system can measure total carbon, total inorganic carbon, total organic carbon, dissolved organic carbon, and total bound nitrogen in both liquid and solid samples. We're also installing a lot of new equipment, and one of these, we've already installed this LGR triple liquid water isotope analyzer, which can be used to quantify the hydrogen and oxygen isotopes in water. And we're also expanding our equipment to include an RMS so that we can also measure carbon and nitrogen stable isotopes. So all of this equipment is available for use. We offer analytical services. So if you're interested in sending samples, you're more than welcome to do so. To learn more about BIOGRIP, you can visit the BIOGRIP website. There you can find out more information about the nodes, opportunities which are available, and how to contact each of the nodes. In the Stellenbosch University website, you will also find us under the Central Analytical Facilities website. And here there is also more information about the equipment we have, sample requirements if you wanted to send your samples, and how to contact us. So here you can find more details about myself and also Ms. Bulante Munsami, which was appointed as a junior analyst in the node. And the last thing I wanted to mention was that BIOGRIP sponsors scholarships or funding for postdoctoral fellows. And the two fellows that have been appointed in the water and soil node is Dr. Wendy Stone and Dr. Jared van Rooyen. And the two projects that they're working on include the evaluation of sewage or sludge, and if this can be used to grow food and biofuel crops, whilst Jared is working on studying the urban isotopes. So I'm sure you'll be able to tell you a lot more about that. And then next year, we're actually going to offer 2 new scholarships. And as soon as we've got those projects information ready, then we will also advertise them on the different platforms so that anyone can apply for these scholarships. You will be appointed as a postdoctoral fellow at the department at Stellenbosch University, and you will be helping us to meet our BIOGRIP goals. Thank you very much.
Thanks, Janine, and a round of applause, please. And I'm sure you can already see it, but Jared will take you through some of the applications and real world case studies and how we can actually use this. And the next presenter is from the mineral node, Robert Hansen. There we go. Thanks, Robert.
Excellent. Okay, good morning, everyone. And I also like to say thank you very much for this opportunity. As Janine and Shafiq has also said, the BIOGRIP is all about collaboration, and this is also one of our main foci. So we also were hoping for more collaboration from this presentation. But yeah, I just want to sort of give a background of where we're coming from and where we're going, so we can also get a good idea of what the mineral biogeochemistry node is doing. We've hosted the mineral BIOGRIP node at the UFS under the Center for Mineral Biogeochemistry, so the CMBG. So from when I speak about CMBG and the mineral BIOGRIP node, they're synonymous. We've also of the Faculty of Natural Sciences has placed people from biochemists and microbiologists from a previous node, not BIOGRIP, but something else, also as part of our team, but I'll get to that in a little while. So without further ado, let me jump into my presentation. So the outline, I'm just going to say a little bit about where we came from, our facilities and equipment, our philosophy and work, and then just have a brief look at some projects that we are doing research on now, and we are looking to do in the future as well. Okay, so in October 19, when BIOGRIP was actually approved, we sat down at the Botanical Gardens in Bloemfontein and started writing the business plan for the center. That is how it was proposed as well, which you can see in the top left-hand corner. And we were very fortunate. There was a building on campus that previously hosted advanced molecular biological research, which wasn't occupied, so we could use that relatively immediately. And here you can see some of our chemicals and things that was put out. This is our vice director, Dr. Marianne Erasmus. She's a biochemist at the university. In her office, as we're packing out, the DNA section, and then just our chemicals now set up. So that was June 2020. Then in March 2021, we would like to have finished all this building and etc. by June. So we did budget for an extension. Here's the building from the outside. You can see they started building, so we had to pack up and move again. So it's been an interesting journey. years, for example, for a day or two, we've got a RO system that treats our water for us, and we needed to do some creative thinking to actually couple it to the water system. It's coupled properly now. And then up to date, you can see this is the picture below is how the center has progressed up to now. And we hope by early next year that we'll be able to move in and make that actually the final move. Okay, so then just some of our equipment and our research facilities. In the top left, you can see an auto titrator. We at Mineral Biogeochemistry are focused on the interaction with minerals, water, and life. And a part of that is looking at absorption. For example, we're specifically looking at arsenic at the moment because of the work we're doing. And as part of that, characterizing mineral surfaces is extremely important. And the mineral surface adsorption capacity is done with titration. At the bottom right, you'll see there's a BET system that we've also purchased, which can measure reactive surface area, but it can also measure average pore size, and it can measure porosity in various materials. So for characterization of mineral samples or sediments in which with minerals that can dissolve and life that can oxidize and reduce things, it's very, very important to quantify the surface areas. And then we've also purchased a microwave digester, which helps us for all our digesting work, because some laboratories, for example, well, at UFS, the water laboratory doesn't do the digesting for you, so we do that for ourselves. And we've also got a lot more control over the digestion phase, which is typically can introduce a lot of uncertainty. And then at the top right, we've also got an anaerobic chamber, which is specifically used to do mineral, water, and life interactions and biogeochemical research in anaerobic conditions. And this is particularly important for us as we're starting to look at wetlands, for example, that are impacted by mining activities. And as the water might be oxidizing, as you go a few centimeters into the sediments, they become reducing. So an anaerobic chamber has become very important for us to be able to do that type of biogeochemical research. Okay, so these are just a few basic constituents or equipment. There's another few planned. In next year or two, we will actually want to start putting together a mobile laboratory where we can service specifically more informal and rural communities, so that we can in real time be able to identify relative water contaminant issues, and then also use that as an education tool to be able to educate the public about water, soil, microbes, etc. Okay, so let's just have a quick look at our philosophy and work. I was very glad to see the network on this conference's logo as well, and that is our primary focus. I think that is the spirit in which BioGrip was done. So we play in the field where we've got biogeochemistry and microbiology specialization in the team, hydrochemistry and geochemistry, and this is then the field of biogeochemistry where we focus on. My specific field or my focus area is water-rock interactions within the mineral part. But we realize that the world has always been complex. We're just realizing, I think, how complex it is, and therefore we are focusing on developing a very small team in-house, and then creating stronger networks with university, with different universities within the BioGrip node, but also outside of that, nationally and internationally. So network and growing our relationship networks and professional networks is extremely important and a big focus of what we do. Okay, so then we've got two main areas in which we are currently doing research. One part is agriculture, bioaugmentation and sustainable agriculture. I'm not directly involved there, so I'm not going to say too much about that. But this project is basically looking at the action of microbes in soil material to be able to enhance agricultural productivity and also the shelf life of agricultural products. So we're specifically working with agricultural companies to be able to do that. And then my focus and the rest of our focus are mostly on mining impacts. This is where I basically came from. I started at the Council for Geoscience quite a few years ago, where I got involved in the environmental section or environmental research for sustainability of mining project. And then I was in consulting for a few years, and all that has been focused mostly on mining impacts. So I'm from an environmental geochemistry perspective. But now we're also looking at bioremediation and community water supply, or at least clean water supply, and I'll be saying something very briefly on that. Okay, so first, we've got patents, for example, for nitrate bioreduction, where we can remove nitrates using a biological process. This is just a picture to show you the pilot plant that we've got at one of our mining sites. And the idea is to be able to expand that to chrome, vanadium, arsenic sulfate, and a number of other elements as well in the future. This is our acid mine drainage plant. We've got a little pilot plant that removes iron, sulfate, and metals. And with the future research we would like to focus on this is optimization of the plant. We're going to add a large bio component so that we can start integrating things like sorption, bio reduction, and that type of thing, so that we can clean polluted water. Okay, and then with the research that we're currently focusing on, this was the start of our biogeochemistry journey, where we've got bringing together different people from different expertise in the teams. At the moment, we're looking at the wetlands in the Welkom area that's relatively heavily impacted by mining and other activities like the discharge of municipal water. So at the moment, we're looking at the quantification of impacts. And then one of the main thrusts is to identify main biogeochemical processes that act in this biogeochemical system, so that we can isolate those bacteria, for example, and combine that with geochemistry, for example, water rock interactions in terms of sorption and mineral precipitation and dissolution, to see if we can use those microbes, for example, sulfate reduction or metal reduction, to engineer, or at least to prove the concept of cost-effective bioremediation water treatment options. So this is looking at specifically cost-effective, because the operational costs, as we've seen with our nitrate plants, for example, are relatively low. And that is going to be a really huge future thrust. And as I said earlier, we also going to put together, the plan is to put together within the next year or two a mobile laboratory, water treatment laboratory, that we can actually analyze water in real time and then give immediate feedback and also education. Yeah, so that was from my side. Thanks very much.
Thanks, Robert and Janine.
Sure.
Maybe when Jared gave us the wow, maybe we'll have some questions and comments and criticism. Good. So without further ado, Jared van Rooyen, who's a postdoctoral fellow under this program, will take us through some of the applications. Thanks, Jared.
Much, and I'd like to begin by just thanking the Groundwater Division as well. This conference has been a really great experience, and I think both us at the BioGRIP node and Janine especially are happy that we get to share this with you and within this community. So my mandate today was kind of loose in the beginning, and because I've been a part of this organization for a while, I've always been grossly disappointed that people aren't using isotopes more. And I didn't realize that it had a lot to do with the analytical facilities that are available to us, the turnaround times when you need to get analysis done, especially for industry applications. I mean, if you take samples out and you only get your data back 3 or 4 months from now, it's hard to tell a client listen, that's the only thing holding us back. And laser spectroscopy has really brought us to the forefront where we can both appease the budgets that academics have to deal with and then the time constraints that industry people have to deal with. And at this rate, especially in our lab, we can process up to 200, 300 samples a week. And if we have two machines online, you can almost double that. And it really, I think this is going to be a new frontier for all hydrogeologists, but especially in Africa, where it's a robust sampling and analytical method. It's affordable and it's quick. So I hope you can tell, but I'm extremely excited about stable isotope research, especially in the context of Southern Africa. But I know a lot of us haven't been as exposed as I have been. So the first kind of part of this workshop, we're going to go through, maybe a recap on stable isotopes. What are they? How do we use them? So what is an isotope in general, right? And this is a concept that a lot of geochemists struggle with at first, then they grasp it, and then they lose it again. But remember, especially the stable isotopes, we're going to behave chemically exactly the same as the element would anyway. And then the slight change in mass, because of the different number of neutrons, forces a fractionation to occur when these elements change phase. So today we're going to be speaking specifically about water. And it's probably one of my favorite ones because it is so robust. The oxygen and hydrogen isotopes are part of the water molecule. And these fractionations only occur when a large amount of water is changing phase. So it can happen on a small scale, but for the purpose of environmental applications, it's really large phenomenons that are going to change the isotopic signature, which is ideal for us, right? We're going to have rainfall seasonality, water coming from different places in different environments and different climates, falling onto the environments that we want to investigate, and then carrying that signature through the hydrological cycle. And we have opportunities to investigate mixing. We have opportunities to investigate recharge. We have opportunities to trace and track different things through the system. And this is something that we can use moving forward. So if we just look at all the different stable isotope combinations we can make for the water molecule, there's protium, hydrogen 1, deuterium, which is heavy water. I think a lot of people see it that way. And then my real baby is tritium, but we're not talking about it today. It's a radioactive isotope and decays rather quickly. And then oxygen 16, most abundant, 17, which is quite nuanced in our research sphere, and then 18. But there's so many different combinations that you can put together. So if you look at when you see a pot of water, I think that's what most people see. When I see a pot of water, this is what I see. It's just a whole lot of water molecules, different combinations of these isotopic, stable isotopes, the heavy and the light ones. And then they interact with one another and they change the phase. And that's the signature, that's the uniqueness of that pot of water. And once it starts boiling, it changes and the vapor that it creates changes as well. So quick summary of what it was. We've looked at it, but it's the interaction between these stable isotopes that we're really interested in. So if we take all the tritium out of this, because it's really so negligible in its abundance and it's radioactive, so we're not going to measure it or use it, we're starting to get a more manageable distribution of the number of abundances. Sorry, I'm not always changing that. Maybe it's a bit of a slower thing, but that's fine. Either way, so you can see oxygen 17, really small amounts, oxygen 16 the most, and then oxygen 18 is kind of what we're interested in. And then the same for hydrogen. Even though it's only 0.2% for the oxygen 18 and 0.01% for the deuterium, these new analytical methods means that we can bring our precision and our accuracy down to a point where we can investigate isotopes that have such a low abundance. But because they have such a small abundance, we need to think about what are the potential different combinations that we can get within the water molecule itself. So let's look at the pot again. What happens when we boil this water? So the original water is there. We have this physical process occurring. We're evaporating the water molecules, and then we're creating a resulting steam or vapor cloud. Now, the steam preferentially uptakes the lighter isotope. So the steam is going to have more oxygen 16 in it and protium, hydrogen 1. And the resultant water in the pot is going to become enriched in the heavier isotopes. So got original delta value, original isotopic ratio in the pots. We evaporate it, got a lighter signature coming into the vapor, but an important concept to keep in your head is that what's left in the pots is being enriched as well. And we're going to talk about how what consequences this has in the natural environment later in this. Sorry, these do jump, but it's fine. We'll figure it out. Okay, so what is the isotope fractionation, right? So there's the mathematical way to calculate it. We're not going to go into today. I don't think anyone's here to relive their lecture experiences. But essentially what we're doing is we're looking for a value that's going to help us predict this fractionation. So we have two different bodies, one being the water in the pots, one being the water in the steam. And there is a predictable, a theoretical fractionation that's going to occur when you put in the energy, you excite the particles, and they leave the system as steam. The only reason I have this slide up is because it's pertinent to the analysis, right? So when we look at a stable isotope laser unit, what we're doing is we're shooting a laser into a chamber. It's vacuum sealed. It's got two mirrors. The laser bounces back and forth, maybe 2, 3, 4, 8 kilometers, depending on your machine. And it starts interacting with the water molecules that you introduce. But now what does it do when it excites these particles? There's different types of energy that happens when you excite a particle, right? We're really into the vibrational, translational, rotational energy. This is what we can measure. Then there is nuclear spin, there's electronic energy that comes. Then we can even go into like quantum realm stuff, but that's not what we're looking at. But essentially, what we're going to do is we excite that particle and then we calculate this Q value that's going to help us determine what expected fractionation would occur and what is the ratio of the heavy isotope to the light isotope. Because when they get excited and refract that laser beam, there's a different response on the unit within the machine. And this brings me to the next step. I'm going to shoot through this because I don't think anyone wants to go to sleep. But we want to get to the applications of it. But this is kind of fundamental, right? We're looking for a 0-point energy. We're looking for a point where we can excite the particle to the point that water's going to boil or precipitate. Sorry, it does. I'm going to stop apologizing. Anyway, so once we reach that 0-point energy, we give an opportunity for the isotopes to leave the system. That's essentially what's occurring, right? And the lighter isotopes leave the system at an earlier time than the heavier isotopes do. So once the particle has got enough energy, it wants to change phase. Now we have an opportunity to create that steam and leave what was in the pot and with the heavier isotopes that are enriching that system. So I think as we move forward, keep it in your head. That's what's happening. As we evaporate things, preferential uptake of the light isotopes, enrichment of the heavy isotopes in the system. And then as we move over and we precipitate out of a vapor source, the cloud, it's the opposite effect. Preferentially, we take the heavy isotopes out of the cloud first, and then we're left with the light isotopes in the vapor source. So now we know that it's all controlled by the masses of the isotopes. Let's look at these different combinations again, right? These 6 different water molecules that we can make using these isotopes. All the way from atomic mass 18, standard 16 protium, all the way up to atomic mass 22, where you have your 18 oxygen and your 2 deuterium as the hydrogen particles on it. That mass difference is really big, and it can create a large fractionation effect, but it is something that we can calculate. Theoretically, we can understand this. So now we're moving our phase transition. We're going from liquid water to vapor water, but the amount of energy to drive this is less if it's the lighter isotopes in the system, and it's more if it's the heavier isotopes in the system. And that's something that we're going to work through and talk about now as we're going to get into the environmental system. I've specifically been speaking about the kinetic effects of fractionation, this movement from one phase to another phase. But it's not always that simple, as we always know. And there is an opportunity for equilibrium isotope exchange. 2 particles with isotopes that aren't undergoing a phase or a chemical reaction to exchange isotopes in the right environments. And this is something that's definitely more pertinent when you're looking at carbon isotopes, nitrogen isotopes, sulfur isotopes. These isotope exchange processes are more the driving factor. But for the purpose of today, we're going to focus on the kinetic stuff. We're going to focus on just water. I think I'm going to skip this example. So now that we've got to our pots, and we're scientists that want to work with these two different phases. We want to start applying them in our research and our applications. We've got to have a standardized terminology, right? This is, I suppose, uniform across all of our fields, and maybe controversial in some fields, I suppose, especially soil and things like that, right? A soil scientist and a geologist go into a bar. But in this case, we report our stable isotopes as a delta value. This delta value is the ratio of the heavy to the light isotope, for instance, oxygen 18 to oxygen 16, compared to a standard. And then we report them in per mole, parts per 1,000. So normally in our sphere, especially the hydrological sphere, we use standard mean ocean water, or SMAO. And more recently, Vienna's standard mean ocean water, VSMAO. And basically, all we're doing is we're saying, okay, well, if you take ocean water, you measure the ratio of 18 oxygen to 16 oxygen, and then you take your analyzed sample and you compare the difference of that sample against the mean ocean water, and then we report it as a value, a delta value against that standard. And what that does for us, it means that we can do research anywhere in the world, in any different situation, but we're all reporting back to the same standard, and we can compare our environments, our climates, our case studies to everyone else as well. And this is where I suppose like the hot words are enrichment, depletion. And it's not really enrichment in the sense that like we're concentrating something. It's only enriched or depleted compared to ocean water, which is a perfect baseline for, you know, environmental studies, because that's where our water comes from and ultimately goes back to. And it's a large enough reservoir that it stays consistent over time, which means we have longevity in our research, right? So the delta value, we're not going to go into the nitty-gritty of how it's calculated, but essentially that's what we're doing, right? It's just comparing to a standard so that our studies can be intercomparable between. So now, because the differences are so small, we're going to times it by 1,000 and report it as per mil. Some people get confused by the symbol, but it really is just there so that we can make it into a value that's like 1 point something, 20 point something, instead of 0.0005 something. Oh yeah, so I wrote a little example here, maybe just to conceptualize it, but a delta value that's 10 per mil is really just saying that it's enriched in the heavier isotope, 10 parts in 1,000 compared to the seawater. And then the opposite, if it's minus 10 per mil, 10 parts in 1,000 relative to the seawater depleted. So let's take a short example, right? So we have an isotopic ratio in the VSMAO, the raw value 0.002. We have a measured isotope ratio from Boston, 0.0019. Now these are difficult values to compute, like work together. And I said, yeah, well, sometimes I read that it's measured against PDB, you know, PD belemnite, which is something that geologists are very familiar with, right? Because they've used it as a standard in other contexts. When we calculate it, me as the hydrologist, well, I say that's minus 15 per mil. And then the geologist next to me says, well, no, it's minus 44 per mil. But see, so the standard makes such a big difference. So I think especially with students, as you start working with this, make sure that you're reporting in the right standard and make sure that you can compare the two or convert the two. It's quite straightforward. So now this is the next step. We want to try calculate the fractionation factor between these two things. So we can measure the isotopes, we can report them as delta values. These delta values means that everybody's speaking the same language. And now we want to try and understand in between the pot and the vapor, what's the difference? What is the theoretical process that's going to drive fractionation? And when we look at this graph, and the only reason that it's here, if you look at oxygen versus deuterium, the two lines that are going down, you can see that they're not exactly the same. There's a small difference there. And that's the temperature gradient that affects deuterium, slightly different to oxygen, which has to do with its mass, its capacity to accept energy. So keep that in mind. I just want to put that in your head now before we start getting to deuterium excess later in this presentation. But there is a direct relationship between the delta values and the fractionation factors. And it can simply be put, the fractionation factor for a situation is the delta value of the source against the delta value of the product. Very simple. We're basically going to change one thing by a certain amount to another thing. delta value evaporates, becomes a new one. So let's look at the hydrospheric reservoirs. Let's look around the world and say, okay, cool, well, most of the water is ocean water. We use that as our standard, so it comes out as zero, delta zero. That's the baseline. Then the ice caps and the glaciers can have extreme variations in their delta values. And that's because the processes that form them are extreme. In the context of our natural environment, the ice caps, it doesn't get more extreme than that. Or it's extremely old. So it came from a very different climate. And we're going to get into these temperature effects, these altitude effects, these continental effects. And then you'll start understanding why they can be so extreme. But for us, we're mostly focused on groundwater. Ranges, I suppose, typically for us, minus 75, minus 40 in the deuterium, minus 5. They're small differences for us, which is great. And then the surface water gets even smaller. So now we have an understanding of what ranges we can expect from our delta values when we measure them. So much so, if you know where you are in the world and someone gives you a random water sample, if you have some isotopic experience there or records, without even knowing where it came from, you can be like, oh, that's probably groundwater. Oh, that's probably a river. Oh, it's got an evaporation signal. Well, it can't be groundwater then. It has to be in a dam. That was a heavy rainfall event. That was a light rainfall event. Or for us, like, we get snow in the Western Cape every now and again. So it's like snow melt. And all the isotope scientists get excited because we're going to see a signal coming through our system. So back to oxygen isotopes. They're normally expressed as 18 to 16. Some scientists turn that around. I don't recommend it. It's going to confuse everything. These observed ranges go all the way from 100 per mil or 40 per mil down to minus 40 per mil. That's kind of what you're going to expect to see in the meteoric cycle. And then there are some weird different processes that can cause hyperenrichments of oxygen isotopes, but we're not covering that today. Okay, so this slide's just here for people to refer back to. If you're like studying for an exam or something like that, take a snapshot, write it on the inside of your pencil case, you'll pass. Okay. So now, if we look at the oxygen isotope variations, we can see as we move through different rock types, we have an expected isotopic signal. And it was mentioned earlier in the Botswana study that the dolomitic, the limestones and the karstic systems might be contributing oxygen isotopes into the water resource. And they're typically much more enriched. If you look at meteoric water compared to where limestones are, that signal is probably quite easy to see. So if you dissolve a whole lot of rock and you start enriching the system, you can probably pick it up. And then it's going to make your normal meteoric interpretations more difficult. So it's just something to keep in mind, that the rock masses that your groundwater is interacting with might, skew your stable isotopic signatures. But these are normally in older systems where the residence time is long enough for the groundwater to pick up the signal. For most of the stuff we're working with, the water's moving through so quickly, it's not going to change the signal enough. And then a very similar thing for hydrogen isotopes, right? We're looking at the fractionation factors at different temperatures. And there we can see this larger kind of change. Sorry, this is the hydrogen isotopes one. Yeah. So now the total fractionation range can get really, really big because the hydrogen isotopes are so small and they get excited so easily. So they're the first ones to run out of the system or run back into the system or change. So that's normally when you're looking at large phenomenon, oxygen's a great way to be, okay, cool, that's one water, that's another one. But when you're looking at secondary processes, evaporation during the rainfall events, extreme humidity above the ocean during evaporation, hydrogen can be a really good indicator for that. So if we look at the hydrogen variations, you can see that meteoric water bar basically covers the entire spectrum. There's enough processes in the world that can force hydrogen to do crazy things that we can expect almost anything from your deuterium values, your delta deuterium values. So the most effective processes that generate these hydrogen isotopes are large events, going water to vapor, vapor back to water, maybe even sublimation from vapor down to ice. And the reason these are different, it all has to do with that energy, right? How much energy can we get into the system? It's got to do with the partial pressure that it's involved in, and then the temperature budget that's going to drive the system. So if we look at the fractionation of hydrogen isotopes, it's got a very different freezing boiling point. Even the pH can affect the fractionation of hydrogen isotopes. And some researchers are actually now using this to find out phenomena that they couldn't investigate before. So how do we deal with this as hydrologists, right? We want to have something to compare our delta values to. And a while ago in the 60s, they developed the meteoric waterline, a theoretical fractionation factor between oxygen and hydrogen isotopes that should naturally occur in precipitation. And this has everything to do with the weight differences between oxygen and hydrogen, and then their 0-point energies. And the meteoric waterline eventually came down to a point where they were like, okay, cool, well, we can calculate this, right? So we take vapor above the ocean. We know that the ocean is starting at 0. We know the expected fractionation factor for the hydrogen and the oxygen isotopes. What are we going to get, right? So you can go through this afterwards, this calculation, but essentially what they've done is they've got to the point where they can say, okay, cool, well, it looks like we're getting 8 times more hydrogen heavy isotopes than we are oxygen heavy isotopes. So we have an 8 factor on hydrogen to oxygen, and then the last portion is going to be controlled by the humidity of the air, its capacity to accept the water. And if you look at the graph here, you can see the global meteoric waterline, the red line. That's hydrogen equals 8 oxygen plus 10. And you can see that most of the rainfall in the area is actually quite similar to that. So theoretically, we're quite sound. And then everything that's pushing us off that line, those are different processes. And that's what we're really interested in as hydrogeologists or hydrologists. What are these processes? How can we constrain them? So we look at this map of Europe, and we can see already what you'd call the latitudinal effect. And this latitudinal effect is driven by temperature, right? You're close to the poles, you get colder, there's less energy, so we have less fractionation. Or like less energy to get the heavy isotopes out of the seawater, put it that way. So we can see in the Mediterranean, we're very close to the seawater value, we're at -4, -6. And as we move northwards, we have a more depleted rainfall signature. And that's because there's just not enough energy. So we're not getting heavy isotopes up into the system. We're depleting the sample actively. And then some other phenomenon that we haven't spoken about yet, but you can clearly see on this map. As we move inland, what's happening? More depletion again. As we move higher altitude, you can see the Alps over there, even more depleted. Now we're getting a cold environment, an inland environment. We're raining out our heavy isotopes as we move onto the continent. And we can see those phenomena. So we're going to look at a whole bunch of maps later on. So here's the delta deuterium worldwide, even better example of this latitudinal effect. Go to the poles, extremely negative values, and then over the equator, very positive values, very enriched values, very close to seawater. And then some that are above seawater. And that's always a big question, right? Why? How do we get more isotopes in our rainfall, heavy isotopes in our rainfall that was in the original seawater? And that is a concept called continental recycling. Remember this, the pot and the steam? If we carry on getting rid of water, eventually what's left in the pot is going to be so hyper enriched that the next steam that comes off is going to be heavier than the sea was in the beginning. And that happens when you stick something on a continent. You have a terminal lake system or something like that. Bring out all the light isotopes until we have a hyper enriched lake. Then the next water that comes off, you're going to have something heavier than 0. So you can see there on the horn, they're having a lot of phenomena that are driving strange isotopic signals. So here's our meteoric waterline, this 8 oxygen, developed by Craig, 1961, but it's not 1-to-1. So we've spoken about that already. I think I jumped forward. So we can skip this. So this is that latitudinal effect that we're seeing, right? Low latitude, more enriched stuff, high latitude, more depleted. And then you can create these lines for all the different places in the world, right? And we can see there in Cape Town, our ratio is 6.8 oxygen, not 8 oxygen. And that has to do with the temperature that we get in the Western Cape. Winter rainfall, it's cooler. The water is evaporated right off the ocean, the Southern Ocean. It's arid above the ocean. There's not a lot of energy. It's not a humid tropical environment. So we're going to drive a different rainfall pattern. We're not going to fall on the same meteoric waterline. And this is something that you gather as you do more data monitoring in your area. You create a signal for your stable isotopes that allows you to apply the same concepts, but in your local region. So these subtle variations are something that's going to help us better understand the processes that are creating the rainfall that we're going to track through the system, and how to understand the research that we're doing, especially in groundwater. Are you getting recharged in the winter? Well, if you are, then you should probably look at your winter rainfall as a likely comparison. And I think I have a big issue when people report mean annual rainfall, especially in isotopes, but actually in general. Mean annual rainfall is if they're receiving, a little bit of recharge every day, but it's not. It's episodic. It's coming in different events, and it's the same thing for isotopes, especially when antecedent moisture is involved. Oh yeah, so I've got this big red thing. I'm going to take a break, have a sip of water, and then we're going to move into the next part, which is going to start heavy science, and then it's going to be very fun. So we just got like 5 slides after this that are going to suck, and then it's going to be more exciting. So I think everyone take a breath. I'm going to have some water and we'll be back in 2 minutes or so. Okay, welcome back everybody. I hope you re-energized. This next step is a concept that took me years to characterize in my head. When I first was explained Rayleigh fractionation, it seemed simple. And then when I started working with it and tried to calculate it, it got less simple. But I think today we're going to keep it super simple, right? So it's a very simple concept. I've actually been kind of inceptioning you as we've been talking, but the concept is once you remove something from a system, you change both the product and the source. That's basically what we're looking at here, right? And the rate of the change between the product and the source is predictable over time, and it'll change in a predictable fashion. The reason we use ocean water as our standard is because the ocean is just so big that it's not going to follow this process. The source of the ocean is going to be constant. But as soon as we move out of the ocean, we start behaving in a Rayleigh fractionation. All this is really saying is we get water off the ocean and it's going to be lighter than the ocean, right? We're preferentially taking up the light isotope. Then your first rainfall event is going to still be lighter than the ocean, but heavier than the cloud it came from. So we go up, we're at 13 per mil, the first rain's at -4 per mil. That's more enriched than the cloud, but it's still lighter than the ocean. So then the vapor gets a bit lighter after it's rained out some heavy isotopes. Now we have a vapor that's at -15 per mil. It's depleting. Then the next rainfall event, although heavier than the cloud, is lighter than the previous rainfall event. So that's what we're going to do. You pick up water, that's probably the heaviest it's ever going to be, and you're going to start dumping heavy isotopes. And as you do it, and as it moves over the continent, that cloud mass gets lighter and lighter and lighter. And that's the continental effect. So if you're more inland, you have a more depleted, lighter isotopic signal. Easy, right? Rayleigh fractionation. Everyone's going to pass. So here's a more in-depth one, right? So now we're going to look at the deuterium and the oxygen isotopic values, and we'll see that they follow the same trend, right? More enriched rainfall the first time, and it gets lighter and lighter and lighter as you move over the continent. And the vapor source will also become lighter and lighter and lighter. But deuterium and oxygen don't behave exactly the same. The deuterium can fluctuate a lot more because those little particles they're excited. They either want to be in, they want to be out, they can't decide sometimes. And then we're going to move on to deuterium excess later. This is how you calculate it. We don't go into it today. I can really see we've got some sleepy guys in the crowd. Now we can use Rayleigh fractionation to calculate, predict what expected isotopic value we'll get either in the rainfall or in the cloud mass. The positives of Rayleigh fractionation, it helps us get the meteoric waterline, right? That's how we can stay on the line, whether we're depleted or very enriched. It's expected, it's theoretical, right? So it gives us the slope. Any like massively large depletions or enrichments, we can characterize them using Rayleigh fractionation. You know, it's temperature dependent. This helps us get the latitudinal effects across the different climates of the Earth. You know, the fact that we have an understanding of the abundance around the world, we can start predicting what kind of rainfall we're going to get and then apply that to our studies. The negatives, we can't really conceptualize deuterium excess and Rayleigh fractionation because we're looking between two different phases. We're going from liquid ocean water to vapor, and then from vapor back to liquid. But if anybody knows anything about clouds here, clouds aren't just vapor. They're liquid water drops in suspension in the atmosphere. So what happens then? What happens when we start transporting liquid across the atmosphere and then just letting them amalgamate and fall out of the system? It's not going to be a Rayleigh fractionation system. We're changing the isotopic value of that cloud without changing the phase of the water. And that's where deuterium excess comes into play. This is the rate that hydrogen exchange can occur during these water droplets' interaction with one another. And it's determined by the relative humidity of the air that's in the environment that the cloud is either forming in or raining out in. And you'll see deuterium excess actually becomes a really great way to understand the humidity of the source of your water. If you have a really high deuterium excess, like, oh, we know it's coming from there on the ocean because the aridity above the ocean in that region correlates to that. And this is where people have said, okay, well, we actually get our rain from that side of the coast, not from this side of the coast. And it helps us as hydrologists constrain our environments. If there's going to be an El Nino event, why did that happen? Well, let's look at the saleable isotopes. Oh, wait, the water source changed. So this is from Namibia. It's an extreme environment. This is still from when Jody was collecting data. And I'm sure she's watching this going, oh, I wish we had done more over there. But essentially what you can see is the light blue dot is the rainfall in Windhoek, right? But the dark blue dots are extreme events in Windhoek. These huge cloud bursts, over 100 mils. And we can see that our local groundwater in the squares is correlating well to that extreme event. So already your qualitative take-home message, well, groundwater is being recharged by the heavy events. A farmer who's been there for 5 generations, he could have told you that for free. But how could you present it to your next funding opportunity, to your next paper? How can you convince them? Well, he has an easy way. This is some data taken from Taiwan, and this is looking at different seasonal effects. Well, we know in the dry season, we have more energy, it's hotter. And so we have a more enriched value. And so all the red dots are pushed up towards the top right-hand side of the graph here. And then in the wet season, we have a progressive change as the temperature changes during the monsoon season. And this helps us understand, okay, cool, well, when is recharge happening? When is this happening? Where on this line is our sample coming from? It gives us an idea in what season that water entered the system. And then we can see a slight change in the deuterium excess of the local meteoric water lines, the blue versus the red line. Same gradient, just one is slightly higher. And this extra deuterium excess gives us an idea of the origin of the water. So there's a slight difference in the seasonality of the two different rainfall events and where they're coming from. So this is before we could use HiSplit to say, okay, well, the water's coming from over there. But it's actually quite incredible how older studies like this could make and investigate such large phenomenon by just collecting a whole lot of 10 ml vials and running them through a mass spec. So let's get to the nitty-gritty, eh? This is the stuff we're more interested in. So let's look at the stable isotopes in Africa, right? So we can see some of the typical effects, right? We get higher and lower latitudes. As you get to a higher latitude, you get a more depleted signal. We see this continental effect. As we move inland across the continent of Africa, so we see a more depleted signal. That's that Rayleigh fractionation we were talking about earlier, raining out the heavy isotopes. And then we see some other interesting phenomena. And this is probably in Central Africa. It's not that it's further inland. It's just that there's more rain. These large volumes of rain are capable of taking all the isotopes out of the system at once. So instead of having heavier signals, you can just dump all the light stuff out at once. And that's why we have that little green dot over there. And then it's a similar concept on Madagascar. Why is it so depleted? Well, it's because of the rainfall amounts. And maybe this might not be the case lately because things have changed a bit there. So I'd like to see probably this done again. Maybe give Shafiq another proposal. Nice. Okay, so a similar thing in Asia, right? We're going to move inland, we're going to get more depleted. We're going to get north, we're going to get more depleted. High elevation, we're going to get more depleted. But then something changes, right? So now we're looking at January versus June, looking at the monsoon season versus the off season or the dry season. And those maps look very different, but the large scale processes are the same. We just don't have the same volume of water to create as clear a picture in the dry season. Australia is a great example of a continental effect. They don't get a lot of rain. As you move inside, you eventually get such depleted values, but they're coming in such small amounts that they're not particularly useful until now. Now we can take a whole lot of samples and we can analyze them really fast. And now they're starting to couple them with radioactive isotopes, and they're realizing that they can constrain the large groundwater systems within Central Australia. Okay, so both the slope, we've spoken about that, it's going to change as you move across the country, and then the y-intercept, the deuterium excess, they're controlled by a variety of factors. So we've spoken about this, the temperature effect, that's that fractionation factor, the amount of rain that's coming down, the continental effect, how much it's been allowed to rain out as it's moving across the system, and then an altitude effect. You know, as you get forced up orographically, it gets really cold, and then we force out more lighter isotopes into the system. So we get a more depleted signal. And this is this influence of temperature, right? So this is just a seasonal thing, January to December. We can see that the stable isotopes mimic the temperature. And this is actually, a lot of people in ice cores have used this concept as a paleothermometer. You know, let's measure the stable isotopes, then we get a great idea of what the climate was like back then. And this is some data that we published, I think last year. I was looking at tritium and its comparison, but on this graph, we can see the stable isotopes from the Cape Town GNIP station throughout the summer, even though there's little rainfall, extremely enriched. And then as we move into the winter and the green bars get higher, here comes our rain, depletion in the stable isotopic signatures. So off the head, everybody knows, what do we expect to see in our groundwater in the Western Cape? The depleted signatures, right? Because that's when we're going to force recharge. Now, there's some interesting studies coming up, especially in the Western Cape, showing a shift in the rainfall seasonality. How is that going to affect our stable isotopic signatures? I think it's going to be very interesting. We might even have an excursion of heavier isotopes into the system. You know, the Western Cape groundwater isotopically might never be the same if we shift our rainfall season by 1 month, 2 months, 3 months later in the year. So this is something that I think it's going to be very exciting moving forward, and it's going to help us constrain climate change, because we know what it has been for the last 60 years. What's it doing right now? Okay, I think we've covered that. Okay, so now when we're moving off the meteoric waterline, when we measure our samples and it's not what we expect, what's controlling that, right? And this is a very simple graph here. Remember the low and the high latitudes, so we know that's how we move up and down the line. And then big precipitation can dump all the isotopes, so we can get up there. And then we have that evaporation trend. This is probably something that we've all seen, right? Everyone takes a sample and they say, okay, well, we're below the line and we're moving to the right. It's clearly evaporating. And that's really helped a lot of us, right? Is the water coming from a sump dam or is it fresh rainfall? If it's got the evaporation trend, that's where it's coming from. And then there's different processes of fluid rock interaction, but this is really only important if you have hydrothermals in your system, which I don't think a lot of us have, but we are working on some hot springs down the Western Cape when we see these phenomena where we move off the line in a lateral sense. Okay, so now we're starting to get to the fun stuff, right? I hope people are still awake. This is something that industry guys can look at. So example, we have a tailings dam. We have a creek that's running nearby the tailings dam. And then we have a spring that contributes water to the creek. So now we're going to take stable isotope data from the 3 different reservoirs. The local spring is clean drinking water. People have been complaining about the creek water. There's a tailings dam nearby. How much is the tailings dam moving into our creek? And is it at safe or unsafe levels? So they take a whole lot of samples, you know, let's say 10 samples from each reservoir. We analyze them in the lab and we plot them on a delta plot. And now the yellow dots are precipitation. So now we have a local meteoric waterline. we understand what we're getting into our system. The first reservoir, that's the spring water, the red one. Then the green one is from the dam. So now we look at the blue one, which is the creek that everyone's complaining about, and we say, oh, well, to me, that looks like a mixing relationship. We have two end members. One is clearly moved off the meteoric waterline. It's got an evaporation signal, the green dots, and it's interacting with the spring. And this is the conceptual model that we've put in before, but now we have unequivocal proof that they're interacting with one another. So the question is, how much are they interacting with one another? And then you can just do a simple binary mixing model. These are measured constituents reported in a standard scale. We can compare them to one another and we can calculate a mixing thing or a mixing ratio. So maths, you can go back and look at it. But eventually we get to the point where we can say we have 45% of the water being contributed by the spring and 55% of the water is coming from the tailings dam. That's extremely concerning, right? And this is something that you'd have to use in your methodology to mitigate what's going on there. We need to make sure that at least half the water that's coming down our creek isn't from our tailings dam anymore, or we need to treat it appropriately so that people can start using it as drinking water. So now when we look at ground and surface waters and how they interact, we can think about how we're going to use these stable isotopes, how we're going to use these delta values to give us insight into something that we couldn't constrain before using other methods. I'm a strong advocate that stable isotopes shouldn't only be used by themselves. It's really hard to tell the picture when that's all you have. So this was a perfect scenario. It's unlikely that you're going to get this in the field. But if you have other data, other methodology, geochemistry, spatial spatial relationships between these two different systems, then you can really use stable isotopes to hammer the point home or to answer a question that you can't quite get the answer to. So now if we look at large systems, in general, the rivers plot along the meteoric waterline, but they can deviate, right? So because the water is moving so fast, you wouldn't expect so much evaporation to occur. But in the right environments, particularly South Africa, like Orange River, you can actually get quite substantial evaporation over the system. So now if we look at the actual plots on the right, we can see the Rio Grande, it's in Mexico. It's really hot, it's really arid, it has an evaporation signal. But then the Amazon, too much water, way too high relative humidity to force lots of evaporation of the river, and it plots on the line. But it plots higher up the line. Why does it do that? Well, here we've got a little cheat sheet. This is one of my favorite schematics that have ever been made. Little cheat sheet. So, okay, well, let's look at the Amazon water and we say, okay, well, it's quite high up the global meteoric waterline. Well, what does the cheat sheet say? It's either warmer, it's a lower latitude, lower altitude, or it's coastal. Well, we know the Amazon is at least 3 of those. Okay, so that explains why it's up there. Why is it still on the line? Well, it's a little bit lower, so maybe it's got a more humid vapor source, right? We haven't moved off the line, so we're not worrying about evaporation, and they get all their rainfall in the summer. So now I've just written a little report on the Amazon River just by looking at a couple of dots on a delta plot and having a cheat sheet next to me. It's the same concept when you start using this in your studies. Put it on the delta plot, get a good idea of the local meteoric waterline. The more information you have, the more interpretations you can make. If you have a bunch of different groundwater samples from different groundwater levels, you have rainfall, you have stream, you have a storage dam, plot all of them on there, and you can really tell a compelling story just by using this cheat sheet in your reporting. So what are some other industry applications? And now these are things that I'm not going to get into today, but we're thinking of maybe translating this into a 1-week isotope workshop next year, where we get professionals from all over the place to talk about all the different isotopes: carbon, nitrogen, sulfur, radioactive isotopes, dating, residence times. But these are some of my favorite examples, right? So mine tailing waters, we kind of had a look at that. Gaining and losing streams. Is it base flow? Is it stream flow? Is it just rainwater? Ocean water ingress. When you see a distinct isotopic signal coming into your system to try and delineate salinization processes. Food provenance. Food takes up the isotopic signal of where it's grown. So you go into Woolies, they say it's from Darling, test it. Not from Darling, it's from Zimbabwe. Like these are real cases. People have gotten into a lot of trouble doing stuff like this. Crisis management. Now this is a little bit dark, and I know this is being recorded, but finding bodies in a natural disaster. They can measure their stable isotopes, where they've been drinking their water, what food have they been eating, and then they can help identify, send them back to their families. So stable isotopes can be applied everywhere. I say beers. I mean, this is something that we all love, or most of us. But, you know, are beers being made with what they say they're being made with? Use carbon isotopes. Are they introducing C4 plants into a C3 recipe? The Reinheitsgebot, they say you can only use certain things to make beer, but the Czech Republic will put corn syrup in, you know, to fast that process because it's legal there, but then they can't sell it in Germany with the same badge. And then also, this is something that I'm looking into, pipe leakages. We're about to put groundwater into the city of Cape Town's water system. Well, that's a new signal for us. Let's monitor boreholes near our large pipe systems. Do we see a signal coming through? Well, it's because the pipe's leaking there. You know, create a heat map. Where can we investigate? How can we save some of our water? These are just some of the applications. And then I say insurance cases here, and I know Julian's watching because we had a conversation about this. But this was a real study. Someone asked me, hey, there's some water leaking in my garage. Where's it coming from? So we took 3 samples, very easy. And we said, okay, well, this is the local rainwater. This is your local tap water. Why is your leaky water all the way over there? Well, it's clearly not the local rain. It could be the tap water, but it's been severely, you know, changed. What's going to do that? A geyser, a heating unit. You know, they've pushed themselves into the evaporative cores. They weigh off any meteoric water we can find in the region. Well, sorry, guys, it's the flat upstairs. Check your geyser. You know, there are other applications for stable isotopes, and it's only limited by your creativity, what you're willing to do. And you to collaborate with other people, find out new stuff. We're seeing such exciting new research, especially in the realm of stable isotopes. And this is something that I know Jody, especially being at the IAEA now, is really punting. She wants more and more African isotope hydrologists. We have better analytical facilities. We have the opportunity now. It's affordable, it's fast return. When we start implementing it, we can only attract more science, more research, more funds. And I mean, I'm coming from that perspective, but even in industry, you know, we can appease our clients. We can give them better insights into what they're trying to investigate. We can disprove some of the preconceptions. Because people will always argue in a physical environment who's right or wrong, but when presented with isotopes, they're not going to lie. I mean, this client couldn't tell me that the leak water is from rain. This is exciting. I'm excited about it. I hope you're excited about it. I know this has been a slog, but I am going to finish 10 minutes early. But yeah, thank you so much for your attention. And please, if you ever have any questions about isotopes, give me a call.
Thanks, Jared. Quite interesting, and I'm sure for a lot of people a nice refresher course. And I know, and I almost wanted to say, you remind me of if I was young when Bolt was around. You probably a young Bolt Verhagen. So we're well done for that, and it's remarkable to see your growth and starting off in WRC projects, and now you're a postdoc fellow, and I guess that is a good example of what we want to do. So we've got a couple of questions. There's one from Robert. You want to answer or ask your question?
Yes, Jared, I was just wondering, in terms of mineral precipitation and weathering and that type of thing, how applicable do you think is, in your opinion, is oxygen, carbon, and sulfur isotopes? I know the work has been done, but I haven't seen any applications of it. So I was just wondering what your opinion is. I'm thinking specifically, for example, in Wits tailings, we've got oxidation of pyrite with a certain sulfur signature. And then would you be able, what do you think one would be able to track, for example, the precipitation of sulfates using sulfur isotopes and oxygen isotopes? Thanks.
Robert, thank you so much. I know I'm not still on the stage, but I can still answer. I think there's capacity for it. It's definitely something that some researchers have investigated, but the efficacy of it in a groundwater environment, I think is quite difficult, right? There's got to be a very substantial exchange between the minerals and the water resource itself. But if you're looking at just the minerals and how they're interacting, especially in a hydrothermal environment, it can be predicted. Whether you can measure it and prove it, I think that's the real question.
Oh, thanks, Jared.
Thanks, Robert. And then we've got 3 from Karen, but she's also in the audience. So let me ask them, is the isotopic signatures of all oceans everywhere in the world in a different depths exactly the same? I guess it's a simple one, so you can take that.
Yeah, Karen, yeah, it's a very good question. I mean, the premise of the theory is that we can use this as a baseline, but no, it's definitely not all the same. And, you know, it's going to be constantly changing, but it changes within a range where for the meteorological cycle, we can assume that it's coming from a very similar delta zero value. But there's definitely very exciting applications of stable isotopes in marine research now, where we're realizing that it's not the same. We can isolate different currents, different areas of the ocean, different uptakes from phytoplanktons, from animals, and trace them as they move through this marine environment. So yes, great question. And no, they're definitely not the same.
Yeah. And I guess the answer is also, it's a mean of oceanic water. So it's a combination of different values. And then the other one is also, have you considered investigating the different types of signatures of different types of aquifer systems?
Yeah, I mean, this is something that needs big budget, right? So I think it's pertinent for us to, the efficacy of stable isotope research in Southern Africa is going to depend on a lot of researchers collecting a lot of data. Hopefully this becomes an atlas one day, an isoscape. If we could have a stable isotope isoscape that's high enough resolution across Southern Africa, you know how much more research we can do. Every single student, when they take a sample, they can refer back to that precipitation isoscape, compare it to the groundwater isoscape. Am I in the system, or is there something different? If there is, why is there something? That just screams to me papers, publications, more applications. Even for industry, I test this. Is it the same as the water well? Let's look at the isoscape. I don't have to monitor rainfall for a year before I can tell them whether it's rainwater or not. We have a database for this. But that's something that we need in the future. And what we need is an uptake of isotopic research in the region.
Okay, yes. And I guess the other answer is also yes. For most systems, we have some sort of study that one can look at in terms of what the characteristics of that system kind of look like. And because remember, it's also a very heterogeneous system. So you can't say that dolomites are going to be all the same, because it depends on whether it gets frontal rain or whether it gets rain from the mid latitudes, as Jared. But it's important to do that. Quick, Karen, we've got a couple of others. Go.
From a pollution investigation perspective, you know, for example, I have a client who gets accused of their landfill site of pollution, but they are located on the contact between Eka and Waal, and which naturally has high sodium chloride. It's very hard, just from a chemistry perspective, to show that it's not the landfill's contribution, but it's the natural contribution. But if I can have isotopes, an isotope map that says, listen, this is the typical isotope signature for Waal, and this is the typical isotope signature for water occurring in Eka, I have a much stronger argument to defend my client against the accusation of pollution. And this is, I mean, really fascinating what you guys are doing. And I think people should, every time they take a water quality sample, someone just take an isotope one for the sake of it, then we'll build up this.
Yeah, thanks, Karen. And I think that's the idea, is for us to, and I've always admired, I don't know whether it's still the same, but in Botswana, that was the rule. Any sample had to have an isotope sample at the company that, and yeah. So we have another one from Kes. And he asks, are the minimum requirements for the number of samples that should be taken per water source that is compared? Okay, what are the minimum samples that one can take, or are there such a guide? Which is clearly no,
Yeah.
but you add a but.
Yeah, Kez, I suppose it's one of those things that's all comparable to the residence time of the source. I think for me, that's the biggest thing. If your source is changing really quickly, like if it's a river, right now you're going to do some monitoring and then understand, how it's moving. And if it's a shallow groundwater, more samples are better. But there's some sources that are moving really slowly. So the stable isotope recipient today will be the same as tomorrow or next week or next month, or even 3 months sometimes, depending on how slowly the water is moving. So rule of thumb, I love duplicates. I love high spatial resolution. I'd say take as many samples as your budget allows, but that's a researcher's answer. Efficacy in industry, I suppose that's got to be situational. But, I'd like to have at least 3 samples to do a 3-point kind of calibration on what's going on. Is it climbing? Is it going down? Get an idea of that. If it's not changing, well, then you're good to go.
Thanks, Jared. And maybe I can just also add, and I think in all your examples, there's that spatial and temporal element to that. And of course, it then depends on what's the objective that you want to do. But I know the other guru sitting there and is putting up his hand. Mic to Roger, please. And while we're waiting for the mic, you and Roger is talking about giving us another book for John Cherry, and because he's been bugging me, but I've already spoken to Roger, so you included now, and you've yeah, I'll go Roger.
Just a quick comment. So stable isotopes, as Jared has shown us very nicely, are subject to all these influences: temperature and humidity and kinetic effects such as wind and how long the reservoirs are in contact with each other for fractionation, etc. So in stable isotopes, we often say that data is very noisy. There's a lot of random, not that variations aren't actually random, but they're due to all these, I won't say hundreds of effects, but loads of different things can cause the stable isotope values to vary. Less so in groundwater, a little bit more in surface water, and extremely high in meteoric, in other words, in atmospheric waters where temperatures and things are moving and changing very quickly. But the point I want to make is that to get a really reliable average for stable isotopes, you do need to have quite a bit of data. 1 or 2 samples is really not enough. For groundwater, you can get away with a handful of samples sometimes if the aquifer is, as Jared says, long residence time, homogeneous, etc. But as Shafiq was just saying, over space and over time, you really need lots of data. So yeah, researchers answer, the more data, the better. But yeah, be careful of taking 1 sample and making a conclusion.
And then a good example is the SMO or the VSMO. It's probably tens of thousands of data points just to get that mean, to draw that line. And I guess that kind of will give you. But again, the question is the context, because it's a great tool also for measuring things relative to something else, like he showed. So often you just want to say, okay, but is it evaporated? And you don't need 10,000 things. If 2 of the samples are way to the left of the small line, then you know what's going on. So, and again, what Jared is saying is that what we're having a problem is the turnaround times in the lab. By the time you try to work out the figure, it's 8 months down the line where you get your samples back, and it might not be the case anymore. So it's a bit complicated, and yeah. So
Does it make sense to take samples at depth, like 1 sample every 2 or 5 meters down a borehole, depending on how deep it is?
I guess if you don't know, then it's a good thing. But over time, if you do it and you see there's not much changes, then you just do the 1. Or sometimes again is what do you want to do? Will an aggregate kind of middle sample give you the answer that you want? But if you do detailed studies for academic papers and those type of things, probably yes. But if you just want to quickly, where's my water coming from? What's the story? A couple of samples is probably the way to go. And maybe Roger, you want to add? Or you finish up? Okay. So we're just on time to, and maybe Karen, you've got Angelo quickly.
Yeah, just in that case where I need a quick answer. Do you prefer, I have 2 deep holes, a few shallow holes. I'll give you a sample of each. Will that be enough to tell me, just give me an indication whether the 2 are can be possibly connected or not? And in that case where I need a quick answer, would you prefer duplicate samples, like 2 samples per hole? What would you recommend in that sense?
Yeah, Angela, I didn't know this was going to turn into an interview, but I am happy to do your research for you. I think you need more than that, right? It's the question in your case is how long is a piece of string? And for us to do that, we're going to need to constrain the rainfall in the area. Duplicate samples are always preferred if you can afford it, but you are in industry now, so you definitely can. And yeah, I'd like to maybe do 2 seasons as well, see if they're changing. And I think, now you're starting to create end members, you can draw a picture.
Great stuff. Thanks for that. But we should also guard against selling isotopes as the tool. It's a tool in the toolbox. So you also need to do your other stuff, the chemistry and your flow lines and all whatever things you want to do. So what we're certainly not saying, Jared, is that isotopes can solve everything. It can solve most, but it's a good kind of what I like to call an integrator. So it gives you that big question or answer to that big question. So without further ado, our next speaker is Jan de Waal, and he'll tell us about how they use this and I left my thing on the table, but it's about nutrients in the Bot River in the Western Cape. Jan, can you hear me, and can you start sharing your screen, please?
Great. Thank you so much, everybody. I trust you can hear me.
We can hear you. If you can put your slides on presentation mode.
I will do. So thank you so much for this opportunity to present. My name is Jan de Waal. I'm busy with my doctoral studies at Stellenbosch University in the Department of Geography and Environmental Studies. I'm already feeling quite good about myself because somebody mentioned that when we're doing water quality monitoring, we should also do stable isotope analysis on the same sample. And I'm feeling good because I've done that. So I'm off to a good start already. I also just want to give a preemptive apology to all the groundwater hydrologists in the room. This is a surface water study. I've been asked by Janine at the BIOGRIP facility at Stellenbosch to present part of my research as an illustrative study of some of the types of analysis that can be done at their facility. So my particular research has focused on the Bot River area, and I'm going to give an overview of some parts of the research, particularly with a view to the monitoring of nutrient content, anions and cations in the river itself. So just as a brief introduction, we know that globally there's a great emphasis placed on the monitoring of surface water resources and the protection of river systems in particular. One of the major threats to the healthy functioning of these rivers is the potential for pollution from agriculture. And agriculture in particular can degrade surface waters through the release of agrochemicals and nutrients from fertilizers that are applied to hill slopes adjacent to water bodies. And these then flow off from these hill slopes into your river system or into your stream, whatever it might be. And this can have a significant impact on the river health. So we can clearly see that there's a great need to monitor the levels of nutrients, the geochemistry or the hydrochemistry of these river systems. So South Africa has got a monitoring network. In 1999, there were water quality data available for over 2,050 monitoring sites in the country. However, by 2009, the National Chemical Monitoring Program monitored approximately 40 primary sites and about 660 secondary sites. And these sites are sampled at a 2-week interval, more or less. And this is important because although we've got an extensive network, there are many more rivers than just this. And so, you know, if we can monitor these systems on a greater spatial scale and on a greater temporal scale, then we can sort of identify what the general water quality is like in these systems and how it's changing over time. So we could basically draw a conclusion that river systems in the country, although we have this monitoring system, are relatively under-monitored. And specifically, we don't get an overview of changing nutrient levels down a river's long profile. Because often we have one sample station which is representative for an entire river. And you know, we know that due to point and non-point source pollution, this might not be the case. The potential for eutrophication of South African rivers is quite high and of a significant management concern due to the potential inputs from things like agriculture. So the purpose of this presentation really is to present the results of a 1-year monitoring of the Bort River system in the Western Cape, South Africa. And I just want to reiterate that this is for illustrative purposes to show some of the analysis that can be done at the BIOGRIP facility at Stellenbosch University, which is the soil and water node. So my primary aim is to demonstrate a baseline of nutrient levels in the river, their spatio-temporal distribution, and assess the potential sources thereof. So just an introduction to the Bort River, for those of you who aren't familiar with it. The Bort River is an example of a river with a closed estuary. And so there are not actually that many of those around. And as such, a lot of the research, historical research on the Bort River has focused on the lagoon itself. So that's the Bort River Vlei. And it's focused on this because it's a very important habitat for a variety of species. And in recognition of the importance of this lagoon, there was actually a major project that was conducted in the 1980s, which was funded by the South African National Committee for Oceanographic Research to assess the status of the conditions of the estuary. And the major focus of this particular project was to determine how opening and closing the river mouth artificially affects the dynamics in the lagoon or in the Vlei itself. However, very little other research has been conducted on the river further up from the estuary itself, or from the lagoon. So this is the Bort River area. Here you guys can see the Western Cape, and let me just put on my laser pointer, that might be helpful. So here's the Western Cape. And the Bort River area is located about an hour's drive east of Cape Town. And this is the watershed over here. And the Bort River has got its headwaters in the Groenland Mountains in the west. And then there's a major tributary which comes from the Caledon side in the east of the catchment, which is called the Swart River over here. Now, what's particularly interesting about the Bort River is that we've got this mountainous region, which is characterized by Table Mountain Group sandstone and fynbos vegetation, and then the low-lying areas, which are characterized by Bokkerveld shales and clay soils, which are traditionally or historically have been covered by Renosterveld vegetation, which is now critically endangered because of agricultural transformation, to a point where about 5 to 10% of the original spatial extent of Renosterveld actually remains. So on this diagram, you can see the monitoring sites that I have selected. So we're looking right down the river's long profile from its headwaters, a few side tributaries, and then down the Bot River itself. Here's another mountain tributary at site 10, and then a major tributary coming from the Grabo area, which is the Jakkalsrivier, and then the shale tributary, which is the Swart River. And here is the Bot River Vlei. So I've taken samples over the course of a year at all of these different sample locations. So the Bot River and its tributaries drain an area that's approximately 900 square kilometers. As mentioned, the major tributaries of the Bot River are the Swart Rivier, which comes in from the Caledon side, and the Jakkalsrivier, which flows in from the west, which is coming from the mountains in Grabo. And the estuary itself is primarily fed by the Bot River. So there is flow that comes from the Swart River, but the Swart River is rather a seasonal river, and it doesn't produce as much discharge as what the Bot River does. There's a Department of Water and Sanitation gauge, gauge G4H014, near Bot River, which estimates that the annual discharge from the Bot River is about 22.6 million cubic meters per year. As mentioned, the underlying geology is Bokkerveld shales in your low-lying areas and Table Mountain Group sandstones in the mountainous regions. And as a result, there are relatively high inputs of silt and other erosion products, especially in your hill slope areas, the low-lying areas. And the shale tributaries often contribute clear waters, but these waters can be turbid, and they can also be very saline, very brackish, as opposed to the mountain tributaries, which the waters are often stained by humic acids, and you get that classic rooibos tea sort of color to these tributaries. I spoke about the degree of agricultural transformation in the catchment, and there's extensive drylands agriculture. So these are oilseed crops and cereal crops, particularly things like canola and wheat, lucerne, few medics, and that sort of thing. Okay, so what is the overall approach? Well, as mentioned, it's been to monitor the nutrient levels in terms of the anions and cations in the river over a year. And the sites were initially selected by examining aerial imagery and then doing a transect to determine where are sites actually accessible in terms of privately owned land versus, next to a bridge or something like that. And this river is quite grown over, and sometimes access to the river itself is very difficult. So the samples were analyzed at the BIOGRIP facility at Stellenbosch using ion chromatography and the stable isotope analysis that Jared has just been describing. So this is a list of anions and cations that are measured by or analyzed by ion chromatography at the BIOGRIP facility. So we've got our anions here, bromide, chloride, fluoride, etc. And we've got our cations as well. And I'm particularly interested in nitrate, nitrite, ammonia, and phosphate, which is basically soluble phosphorus, because these are your primary fertilizer inputs. So here you guys can see, thank you to the Department of Water and Sanitation for their streamflow data, but streamflow data from the Rooyen gauge from October 2020 through to September 2021, the last month's worth of data haven't been processed yet, so I haven't been able to include that. And then these black dots are the times where I actually was able to go out and collect samples at these different monitoring sites. So you can see there's a clear signal in terms of stream flow, where the Western Cape is characterized largely by winter rainfalls. And so it's generally from May through to October that we see rainfalls falling here in this system. And from November through to April, we have our dry season, and stream flows are pretty low. So the first thing I wanted to do was to characterize the local conditions. And I did that with a bulk density plot for your stable isotopes, a bulk plot. And here you guys can see in blue, we've got some precipitation samples, which we have produced a local meteoric water line. So that's our regression line through those. I do have a few more precipitation samples that still need to get analyzed. And I just want to reiterate what Jared was saying, that the turnover time for this analysis has been really good. So, you know, if I submit my samples one day and I get the ion chromatography results the next day, and the stable isotopes, you know, are run when the machine is run, and basically as soon as that analysis is done, it's sent to me. So the turnover time is really quick. In red, we've got a whole bunch of river samples. So these are samples taken at all of the various sites. And we've got our regression line over here. And this gray line is our global meteoric water line that Jared was talking about. So that's that delta 2H is equal to 8.13 delta 18O plus 10.8. So when we look at this pattern, we can see that our local meteoric water line has got a very similar gradient to the global meteoric water line, but it has got a greater deuterium excess. When we look at the river samples themselves, we see that the gradient of this regression line is slightly lower than the global precipitation or the global meteoric water line. And so when we look at this, we see that the local deuterium excess in your local meteoric water line suggests that the rainfall is coming from a more arid vapor source. So as Jared mentioned, a slightly colder ocean. And so this is very typical of patterns in the Western Cape where, you know, we have the formation of mid-latitude cyclones and cold fronts over the Southern Ocean, which is relatively arid in comparison to your sources at lower latitudes. The river samples with a lower gradient, so that's this red line over here, shows a signal of evaporative loss, which is consistent with the semi-arid conditions present in the Bort River catchment. So the mean annual precipitation in the Bort River catchment is roughly about 500 millimeters a year, although in the mountainous areas, this can increase up to about 1,200, 1,300 millimeters per annum. So let's focus now on the water chemistry. So these are the results from the ion chromatography. We see that in general, our shale tributaries show a substantially higher salt content. And there is a major influence of the Swart River on the Bort River's water chemistry downstream of the confluence of that tributary. In general, nitrite, ammonia, and phosphate levels were very, very low and often below detectable limits in the river, but nitrate was a lot more prevalent. So this is a table, which is, I see it's been cut off on my screen. I hope hopefully it's not cut off on your screen, but you guys can see we've got all of our different sites, so site 1 through to 15, and we've also got the different ions that are listed over here. And you guys can see, particularly in relation to nitrate, which is this line over here, that we do certainly have nitrate in the river, nitrate present in the river. And I want you to focus on site 14, which is the Swart River. And this, you can see that the nitrate levels are considerably higher. The nitrate concentration is considerably higher than the concentrations from elsewhere along the river profile. And this then influences the water chemistry, the nitrate levels lower down in the Bort River after the confluence of this tributary. So site 13 is before the Swart River has come in, and our mean nitrate concentration there is about 3.13 milligrams per liter. This is obviously variable seasonally. And then the Swart River comes in, and then it increases to 6.62 milligrams per liter. So really the Swart River is contributing a lot in that regard. When we look at sodium and chloride, we see that these concentrations are very high. And I want you to focus on these areas marked in yellow, those are your shale tributaries. So S1, S2, S7, and S14. And we see here that the chloride and the sodium levels in these shale tributaries are considerably higher than, for instance, these areas in green, which are coming from mountain tributaries themselves. So the mountain tributaries are contributing fewer salts than the shale tributaries, which are from these clay-derived soils, or these shale-derived clay soils, should I say. If you look at the nitrite levels are pretty low in general. Ammonia levels also pretty low, often below detectable limits. And the phosphate levels also often below detectable limits. However, there is a seasonal sort of signal to this as well. And so here you guys can see the spatial distribution of our mean NOx nitrogen contribution. So that's nitrite plus nitrate, and just taking the N in those compounds. And so you guys can see that in general, we've got quite a high level of NOx right immediately in our headwaters over here. And then we also see that the Swart River contributes quite a lot. And the mountain tributaries, so site 5 and 10 and 12, contribute relatively little in terms of your NOx-N. Now, I know that I've made the cardinal error of trying to put too much information on one diagram, so this was probably quite small. And I don't want to focus on it too long, but I want to show that for these sites, so this is October through 2020 through to October 2021, there is a strong seasonal distribution to NOx in concentrations in the river. So where there are missing data, that's basically when these streams or tributaries dried up, so there wasn't flow in those particular months. And you guys can see that basically during our winter months, there's a strong increase in concentrations of nitrogen in the river. In particular, there's a massive jump in nitrogen concentrations in May. And the reason for this is in early May, there was a very strong cutoff low that came through the Southern Cape. And this cutoff low dumped precipitation in the lower end of the catchment. So the southern coastal part of the catchment was about 200 millimeters in 2 days. And then higher up in the catchment, it was about 150 millimeters over 2 days. So it really was a massive event, a real sort of first flush to the system, and we saw a big nutrient response. So if we look at the seasonal pattern to nitrogen in particular, we see that in the dry season, so this is November through to April, your NOx levels, your nitrogen levels are pretty low. In fact, they are all below 400 micrograms per liter of your water. And that's really important. De Villiers and Tiart basically report that 400 micrograms per liter as being a cutoff for, basically waters that have got enhanced nitrogen levels. If we look at our wet season, so this is now May through to November, these nitrogen levels jump by a whole order of magnitude. And we see in particular strong nitrogen inputs from site 2, site 7, and the Swart River itself. And these are generally areas that are characterized by agricultural land use. So the areas that are in orange in this land cover map are cultivated commercial crops, non-pivot. And so you can see that these rivers or these tributaries are draining areas that are often covered by these cultivated fields. And so we could plot this graphically, and we see a seasonal variation in our NOx-N. And basically we see that for the dry season, which is in red, the average or the mean NOx concentrations are well below this 400 microgram per liter mark. And then for the wet season, they are well above this level. So what about phosphorus? Well, as mentioned, in much of the catchment, phosphorus levels were below detection limits, except for, once again, the Swart River. So the Swart River, I remind you, is this river coming in from the east, which is from the Caledon side, and it drains this area, which is characterized by cultivated commercial crops. And so here you guys can see the changes in soluble phosphorus concentrations over time, and we see in the winter months an increase in PO4 levels, and these levels exceed the 100 microgram phosphorus per liter maximum recommended, which is the recommended water quality guideline for aquatic animal life. So we see here that certainly we have exceedances of this, which arise episodically, certainly in your winter months during rainfall. So what conclusions can we draw here? Well, we can conclude that the Swart River is particularly influential in terms of overall water quality and the nutrients that are flowing into the Bort River Lagoon. And this is probably a result of land use. There are brackish waters that are contributed from your shale tributaries. There's a substantial seasonal variation to nitrogen loading in the river, where nitrogen loads increase by an order of magnitude between your dry and your wet season. And this is expected due to the solubility of N on your agricultural fields, the application of N to your agricultural fields in your sort of May month, just preceding the first rains. This is particularly important because it results in nutrient loading of the river. However, in the Western Cape, we have winter rainfall, and so the nitrogen loading coincides with lower seasonal temperatures, and so we don't see much evidence of algal blooms in particular. Soluble phosphorus is generally below the detection limits except for the Swart River, and we could sort of conclude that all of the sites except for site 5 and site 10 can be classified as impacted by nutrient loading, particularly in relation to nitrogen during the winter season. And these nutrient fluxes can be associated with significant losses to fertilizer equivalent nutrients from your surrounding hill slopes. So yeah, thank you for listening to my presentation. And I hope that for all of you who are involved in these sorts of analyses, particularly in groundwater, use the BIOGRIP's facilities. They've really been phenomenal to me. And I just want to thank Janine and Valenti and Jared for your wonderful help in my studies.
Thanks, Jan. Round of applause. And I think you apologize for coming to a groundwater conference. So I'm going to ask the question that's certainly on everyone's mind. You are sure there's no groundwater input into any of these things?
I'm 500% sure that there is groundwater input into these things, but not part of the sort of remit of my study. And maybe it's something for future studies, is to measure, how much groundwater input is coming into the system. Something that I didn't present here today because it's not really a BIOGRIP product is that we have been developing a hydrological model using JAM software, which has modeled the relative groundwater and surface flow contributions to overall stream flow and discharge in the river. Yeah.
Thanks, Jan. And I certainly think you need to consider that. But any other questions in the room? No? And maybe if Janine, you're still around? Or Jared is here, so maybe I can ask Jared, we've got 1 minute, is that in terms of the BIOGRIP facilities, and while you guys were talking, I fondly remembered my days in Chris Harris's lab at UCT, and this is where Roger also came from, and doing your own sample prep and thing. So do you guys allow other people coming to cook in your kitchen? Or how does it work? Is it just a sample delivery?
No, Shafiq, you
Sound?
Shafiq, you're 100% correct. The BioGRIP facility in general, we're there for capacity development. Training is in the mandate. And because the soil and water node forms part of the central analytical facility, we're literally condoned to include all students who are doing analysis through our laboratory to come and learn how to run the machines, process their own samples. COVID has put a spanner in the works, but we now, especially if students are coming, we can separate them to different times. So it's encouraged and almost mandated that people receive training in the lab as well.
No, that's great. And I think any student must take up that opportunity. It's fulfilling, but you also learn a lot, and you learn how to not just take samples in a Coke bottle. I see you guys, but also do it the proper way. But also just talking to the lab guys, because they know all the tricks and they've gone through a lot of these things. So well done. So if there's no other questions, I think we can end. Okay, there's one question there, and maybe get a, and it's going to be a quick question.
Thank you. I want to ask you about something which is outside your territory. I want to ask you something about RBS Pordem, the presenter. RBS Pordem. What is it that government can do to reduce the nutrients in RBS Pordem?
That's going to be a discussion for the break. So we're going to stand around the table, have some coffee, because we're reconvening in 30 minutes. Sorry? They said 3:15. I just want to thank everyone that's in the room, that's on the various platforms. Thank you for making this available. And certainly, I think just because we're almost talking to a small community within the sector, but I think we need to take this message much wider as well. And so I think that there will be other initiatives. So we see there's a need, and the interest is there. So thanks to all the BioGRIP guys at all the notes. And with that, the session is closed. Thank you.